Hello everyone, I'm Ingénieurs.pedraza, PhD of ENTPE School Associate with Lyon University in France. I will talking about our properties at low temperatures of warm mix contain high content of multi-recycled wrap. Thanks to Mr. Di Benedetto, Mr. Sosea and Mr. Puget for your collaboration in this paper and during my thesis. So, in this first part, I'm going to present the outline, the context, tested materials and multi-recycling process, then the thermal stress restrained specimen test, wrap, recycling cycle and air void content influence, and finally the conclusions. According of the balance sheet of French industries road unions, the use of reclaimed asphalt pavement wrap increased during the last 10 years in France. However, the binder not recycled represent an economical and environmental loss. For this reason, ANR, National Agency of Research in France, create the MURE and IMPROVMURE projects to promote use of wrap, use of new manufacturing process, and to test a wrap with several recycling cycles. This project has scientists and industrial partners. You can see here the organigram of projects. The budget of IMPROVMURE is 2.3 million euros. The IMPROVMURE project is the scientific part of the MURE project. FH and ENTPE School, in collaboration, take care of the thermomechanical characterization of bituminous mixtures. The difference between bituminous mixture are wrap content, 0%, 40%, 70%, and 100%. The second one, process, hot and warm. And the last one, production, laboratory conditions and in situ conditions. In this presentation, we will see the properties at low temperature of three warm bituminous mixture of studied bituminous mixture. In this part, I am going to present tested materials and multi-recycling process. Materials. 3 warm bituminous mixture of type BBSG 3010 according to European standards were used to this study. The bituminous mixture were produced under laboratory conditions using a foamed bitumen. The first one bituminous mixture were produced without wrap. The second one bituminous mixture were produced with 70% of wrap, one recycling cycle, and the binder added 160-220 penetration grade. The last bituminous mixture used 70%, 3 recycling cycles, and the same binder added. All bituminous mixture had fixed parameters. The first one grading curve is the same. Total binder content is the same. And finally, aggregates and filler addition are the same. Now, I'm going to present the fabrication of bituminous mixture with a wrap and manufacturing of samples. So, the first bituminous mixture with a wrap was manufactured with aggregate and binder with 35-50 penetration grade. Mixing these components, we have a bituminous mixture not compacted. Then, this mixture was subject to a compaction process. And finally, we have the bituminous mixture reference without wrap. Using the French well compactor, one slab was made for each bituminous mixture. From each slab, 5 cylindrical specimens were cored and sewn. You can see here the dimensions of a specimen to test. Now I'm going to present the second one, bituminous mixture, with 70% of wrap and 1 recycling cycle. The wrap introduced in this bituminous mixture came from a milling process. This wrap was mixed with aggregates and a binder 160-220. The result is a bituminous mixture not compacted. Then of compaction process, we have our bituminous mixture to test with 70% of RAP and 1 recycling cycle. Here I am going to present the last bituminous mixture with 70% of RAP and 3 recycling cycles. This bituminous mixture used the same process of the bituminous mixture with 1 recycling cycle. But when we have the bituminous mixture not compacted, we take this material and this sample is subjected to an aging process. The procedure consists in warming the sample at 135 Celsius degrees for 4 hours and at 85 Celsius degrees for 9 days. The resulting material is considered as RAP with 2 recycling cycles. This RAP is mixed with the same aggregates and binder to produce the second one, bituminous mixture not compacted. And finally, this material is subjected to the same aging process. After that, the resulting material is considered as a RAP with 3 recycling cycles. This RAP is mixed again with the same aggregates and binder. So we have the bituminous mixture not compacted with 3 recycling cycles. And finally, this bituminous mixture is subjected to a compaction process. So we have our bituminous mixture with 70% of RAP with 3 recycling cycles. This is the multi-recycling process. In this part, I'm going to present the testing device of the Thermal Stress Restrained Specimen Test. So we have here our cylindrical specimen. This sample is fixed to hydraulic press, and to measure axial strain during the test, 3 extensometers were located around the specimen. A thermal gauge is fixed to obtain the surface temperature. The thermal chamber is used for the thermal conditioning of the sample during the test. The testing device was calibrated to avoid the error due to the cooling introduced during the test. You can see here a typical experience of thermal stress restrained specimen test. The principle of TSRST is to keep the axial strain null while decreasing the temperature inside the thermal chamber. The test starts with an initial temperature, 5 degrees. After that, the specimen is subjected to a cooling. Cooling causes a contraction of a specimen. However, the hydraulic press prevents this. Therefore, a thermal stress is induced inside the specimen and increases until the specimen breaks. You can see here the stress as a function of the temperature during the test. When the specimen breaks, we have failure stress and failure temperature. You can see here the repeatability evaluation of bituminous mixture without RAP. We use the stress as a function of temperature during the test to evaluate the behavior of the samples. You can see the 3 curves superimposed. The other mixture present the similar superimposition. That means an excellent repeatability between the sample of the same bituminous mixture type. Now I'm going to present the RAP and recycling cycle influence. For this analysis, the temperature failure was averaged, and you can see here a histogram of the temperature failure average of type mixture obtained. Also, you can see here a histogram of the failure stress average of type mixture obtained. The histogram's quantities of RAP don't show a significant impact of the temperature failure and stress failure average of materials. However, in the first analysis, this change of the stress failure appeared to be due to the introduction of RAP. But in the second analysis, the air void content was evaluated. The stress failure was plotted as a function of the air void content for each sample tested. We can see that the stress failure shows a linear tendency according to the air void content, with a negative slope. As the sample of bituminous mixture contained RAP present a lower air void contents than samples of bituminous mixture without RAP. So, the increases of stress failure was due to the air void contents of samples and not RAP content. Conclusions. TSRST was used to study the mechanical behavior of bituminous mixture at low temperature by thermal coupling. The evolution of the stress as a function of temperature during the test of the sample tested showed superimposed curve for each bituminous mixture. That means that the sample of the same bituminous mixture have similar behavior. Analysis of temperature failure and stress failure. The temperature failure showed similar values obtained. In consequence, the addition of RAP didn't have a significant influence. Failure stress presents a linear decreasing tendency with air void content. And finally, the foamed bituminous mixture with multi-recycling RAP have good behavior by coupling thermal and mechanical effects at low temperatures. Thank you very much for your attention, and I invite you to subscribe to my YouTube channel in Spanish about the roads. Thank you very much.